Okay, so we're going to do a 3x3. We're going to do a 3x3 example of diagonalization. So let's diagonalize. The matrix A with A equals to 1, 1, negative 1, 0, 2, 1, 0, 0, negative 1, let's say. And so what we need to do is we need to find a matrix P such that P to the negative 1 AP is a diagonal matrix, and we can be very specific. I mean, finding the eigenvalues of this matrix is pretty straightforward because it's triangular. So its eigenvalues are just 1, 2, and negative 1. So this would be 1, 2, and negative 1. So we want to make it this way. Okay. And actually, let's make a note and see that this is the right thing, because we know that the characteristic polynomial can be taken to be the determinant of the matrix X times the identity in 3 dimensions here, minus A, which is what determinant? It's the determinant of X minus 1, negative 1, 1, 0, X minus 2, negative 1, 0, 0, X plus 1. And since this is a triangular matrix, we will get that the determinant is X minus 1, X minus 2, X plus 1. And if you set P of X equal to 0, then you will find eigenvalues 1, negative 1, what is it? I'm sorry, 1, 2, and negative 1. Okay?
Okay. So do we try to get it, like, when it comes to the form, do we try to get it where there are 3 zeros at the bottom or top? Is that what makes it easier?
The pattern, the desirable pattern here is diagonal. So you want anything on the diagonal, or you allow any number in the diagonal. In this case, it's not just any numbers that are going to be there. It's specifically the eigenvalues that are going to be there. And then everything else, every off diagonal entry has to be 0. Okay?
Okay.
So now we need to work with every eigenvalue. So we start with the eigenvalue 1. So what we need to do is take this matrix right here and find its null space, because the null space of this matrix is going to be precisely the space of all eigenvectors. So I take this matrix. So what do I get? I get a 0 here. I get minus 1. I get 1, 0, minus 1, minus 1, 0, 0, 0. No, 0, 0, 2, sorry.
Okay, that's when we plugged in, left it.
I plugged in, and I also put the extra row because I know that I want to solve a system. So I want to bring this to row echelon form. Okay. So now look how the first column doesn't have a 0. I'm sorry, doesn't have a non-zero. So there's no pivotal element. What does that mean? That means that we need to proceed with the second column. And for the second column, I'm going to turn this into my pivotal. And the way to do this is by performing negative row 1. So by negative row 1, that entry becomes 1.
Okay.
And now that that entry became 1, I can eliminate the negative 1 underneath. How? By adding row 1 to row 2. If you like, that's the same thing as saying 1 times row 1 plus row 2. And this will be 0, 1, negative 1, 0, 0, 0, negative 2, 0, 0, 0, 2, 0. So we're done with the first column, the second column, and the first row. So pretty much what you're working with, the way you think, you need to think in terms of the Gauss elimination method, is that you're working with this part of the matrix. So again, you need to create a pivotal on the third column. And the pivotal on the third column is going to be created by negative 1/2 row 2, which is going to give you 0, 1, negative 1, 0, 0, 0, 1, 0, 0, 0, 2, 0. You have your pivotal, and you can eliminate that too by doing a negative 2 row 2 plus row 3. Okay? And this finally brings our augmented matrix into row echelon form. And now that we have it in row echelon form, we go back to our variables. So there's no x. Okay, you have 0x if you like. And right away, you know that x is going to be free because there is no pivotal element. So you have y minus z is equal to 0, and z is equal to 0. And this tells you right away that both y and z are 0, which means that the vectors in your null space, in the eigenspace, if you will, look like x, 0, 0. And you need just one of them. And I can take just the 1, 0, 0. So that's my first eigenvector. That's the first eigenvector. Any questions, please, on this?
Okay, so you reduce this y minus 0, y minus z equals 0 to y minus?
You always start from the bottom one. So I started with this one. So if I know that z is 0, I put it into the top one, and that gives me also that y is 0. Remember?
Oh, gotcha.
Whenever you get your equations from the row echelon form of the Gauss elimination method, you actually always start from the bottom equation. You always start with the bottom equation, and then you go through pretty much all the equations upward. Okay?
Okay.
Now let's do lambda equals to 2. If lambda equals 2, again, I'm going to go to my matrix with that one with the x's, and I'm going to see what I'm getting. So I'm getting 1 here, then I'm getting negative 1 and 1, then I'm getting 0, 0, negative 1, and then I'm getting 0, 0, 3. That's what I'm getting. I make it into an augmented matrix. Really, the last column that I'm putting there is never going to be used in those steps. I mean, somebody might say, well, can't I just skip that part, that column? I mean, that column is constantly going to have zeros in this computation. And the reason why I'm saying, no, keep it there, is to remind yourself that we're solving a system here. We're finding the null space. It's not just always, to do things from a procedurally simpler perspective. It's also to understand what we're doing. So we're trying to find the column vectors that, when multiplied by this matrix, gives you 0. To do that, we need to solve the system, the homogeneous system, meaning the constants on the other side are all zeros, which means that what you add is going to be just the column 0. Again, it seems useless, but it's very much important to keep it there so as to remember that we're solving a homogeneous system. So your pivotal on the first column is all set to go. There's nothing to do there. Now remember, once you have, and everything underneath is eliminated, but when you go to this part, you can see right away that here you have 0. So there can be no pivotal in the second column. What does that mean? You move on to the third column. In the third column, you're going to make this pivotal. So that will be minus R2. And this will give you 1, negative 1, 1, 0, 0, 0, 1, 0, 0, 0, 3, 0. And now you eliminate the 3. So you do minus 3 row 2 plus row 3. And that gives you 1, negative 1, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0. This is row echelon. What is the system behind it? X minus y plus z is equal to 0. And remember that y is free. Y is free. So you get that z 0. And since you know that y is free, you set that z equal to 0 and you solve for x. And that gives you x is equal to y. And y is free. So this means that when you write down your solutions, x is the same thing as y is free, and z has to be 0. And this gives you your second vector, which is y times 1, 1, 0. So the second vector that we got, the second eigenvector corresponding to the eigenvalue 2 is equal to, okay?
Okay. Why? Okay, and then. Okay, that makes sense now.
Okay, let's do the third now. Let's do the third one. So for the third one, we have to plug in, again, when I say plug in, I mean in this matrix right here, we have to plug in negative 1. So when we plug in negative 1, what do we get? So for lambda equals negative 1, we get negative 2, negative 1, 1, 0, negative 3, negative 1, 0, 0, 0. Okay, let's see if we can negative 2, negative 1, 0, negative 3, negative 3, negative 1. Let's see. Negative 2, negative 1, 1, negative 3, negative 1, 0, 0, 0, 0, 0, 0, 0. Make sure that this is right. Yes, this is right. Okay. So let's solve this. We need to create a pivotal on the first. So I'm going to do negative 1/2, row 1. And that is going to give me 1, 1/2, negative 1/2, 0. The other columns remain as they are. And the first column is all set. The first column is all set. There's nothing more to do on that column.
Okay.
So we go to the second column. And when I say the second column, again, it's important to remember that you work with this portion because you have already worked with the first row. And you need to make that negative 3 pivotal. And how do you make that negative 3 pivotal? By doing negative 1/3, row 2.
Okay.
And that gives you 1, 1/2, negative 1/2, 0, 0, 1, 1/3, 0, 0, 0, 0, 0. Now, when you leave behind you the second column and the second row, unfortunately, you have only zeros. You're done. There is no more pivotal. You have 2 pivotal elements. You're all set, and you can go to your variables and find the x and the y's. So we do that. So we do x plus 1/2 y minus 1/2 z is equal to 0. Which one is the one that is going to be free? Because you need to have a free unknown here. It's going to be the one, the variable corresponding to the column that doesn't have a pivotal. So meaning z. And then you have y plus 1/3 z is equal to 0. And here y is going to be equal to negative 1/3. So we always start with the bottom one. Now we take this negative 1/3 z and we plug it into the first one. So that will give us x minus 1/6 z minus 1/2 z is equal to 0. Now we need to add 1/6 plus 1/2. That's the same thing as adding 1/6 plus 3/6, which is 4/6, which is the same thing as 2/3. So this is x minus 2/3 z is equal to 0, which means that x is equal to 2/3 z and z is free. So now we solved our system. So here's the solution. Okay.
Honestly, I just got to that section, to that column with the y equals negative 1/3 z. So that was, first you simplified.
Right.
I'm trying to see what you did after you label.
Once you know that y is equal to 1/3 z, you pretty much take this thing and put it in the place of y. And when you put it in the place of y, you get negative 1/6 z. And then you just isolate it. Okay?
Okay, that makes sense now.
And now we can put together the eigenvector, and the eigenvector is going to be 2/3 z, negative 1/3 z, comma z. And you know what, you can write it here. We have a very interesting situation where you can write it as 2/3, negative 1/3, and 1. And I don't want to work with denominators, so I'm going to just set z is equal to 3, and that is going to give me the eigenvector 2, negative 1, 3. And that's the eigenvector that I'm going to get. So now I think I have everything together. I remember I found 1, 1, what was it? I found 1, 1, 1, or was it? Oh, no, 1, 0, 0, then 1, 1, 0. Let's take a look at that. So we found 1, 0, 0, 1, 1, 0, and finally we have this one. So if we put this together as columns for our matrix, that is going to give us the column, the matrix P. So 1, 0, 0, 1, 1, 0, and 2, negative 1, 3. And what is it that we need to do in order to finish? We're almost done. I mean, go and take a look at what we were trying, what we set out to find. We said we wanted to find P and P to the negative 1. We have our diagonal matrix, and all we need to find is P to the negative 1. Once we know what P to the negative 1 really is, then we will be all set. So, yeah.
So how did we get the z value for
the z value is completely arbitrary. I just chose 3. I mean, if you look at the previous cases here, when I found this, what did I take really? X equals 1. That's why I disregard 1 and I keep the 1, 0, 0. Here, I took y is equal to 1 because the eigenvector that I had right there, the 1, 1, 0, is already very nice. But if you go to this last case that we had, the eigenvector that I had, at least the one that emerges, has this nasty denominator 3. So I want to get rid of that 3. So what do I do? I chose z equals 3. You know what? It's not a problem if you chose this eigenvector, if you chose 2/3, negative 1/3, 1. I'm just going to get a matrix P that has integral entries. I'm going to pay the price later, meaning when I find P to the negative 1, that is going to have denominators. Okay, now if for example, you took the third eigenvector to be 2/3 minus 1/3 1, then maybe you would have had your denominators at this point, but when you found the inverse matrix, maybe you wouldn't get a denominator there. So there's always a trade-off here. Okay, you cannot, the bottom line is I cannot avoid denominators if they're supposed to show up. So to find the inverse of P, we set it up with the identity matrix on the left. And what am I targeting now? So this should become pivotal. This should become 1. This should be 0. That should be 0. And eventually that should be 0. That's exactly what I'm targeting right now. So I have, I make the last one pivotal, so 1/3 row 3. And this gives me 1, 1, 2, 1, 0, 0, 0, 1, negative 1, 0, 1, 0, 0, 0, 1, 0, 0, 1/3. Okay, now I have my pivotal. I'll use this pivotal to eliminate, because remember when you do the reduced row echelon form, you always start with the last column. So I'll start with the last column. I'm going to eliminate -1 and -2. So what am I going to get? I'm going to get the last row remains as it is. And then I get 0, 1. Oh, I'm sorry, I didn't write down the row operation. So it will be row 3 plus row 2. So I'm adding row 3 to row 2. And then I will do -2 row 3 plus row 1. That's how I'm going to eliminate those two numbers. So I will have 0, 1, 0, and then 0, 1, and 1/3 right here. And then I will get 0, 1, 0, and 1, 0, and then -2/3. And finally, I want to eliminate the second entry from the first row. So I'm going to do -2 row 2 plus row 1. And this will give me 0, 0, 1, 0, 0, 1/3, 0, 1, 0, 0, 1, 1/3, and finally 0. Oops, why did I say 0? This one. Okay. 1, 0, 0, 1, 0, and now finally I will have -2/3 plus another -2/3. That is going to give me -4/3. And no, there's something more. And this will become a -2. Oops, yeah, because I'm adding row 2, -2 row 2, so -2. Okay, that is now correct. Okay, so what is p to the -1? So p to the -1 is going to be 1, -2, -4/3. It is possible that there is a mistake. I'm not saying that it's impossible that there is a mistake, but I hope there's no mistake. And now we can put the whole equation together. We're all set. And what is our equation? So we will have 1, 1, 2. So 1, 1, 2. 0, 1, -1, 0, 0, 3. Excuse me. 0, 1, -1, 0, 0, 3. That's P. Then in the middle, we should have our matrix, which was 1, 2, -1. Then there was an 1, -1, 1, 0, 0, 0. Let's see if I remember this correctly. Yes, that's right. And finally, we have p to the negative 1, which is 1 negative 2 negative 4/3. 1 negative 2 negative 4/3. And then 0 1 1/3 0 0 1/3. 0 1 1/3 0 0 1/3. And we know because of the order in which we chose our eigenvalues, this is going to be 1. Remember, we did first 1, which means that the eigenvector that we put right here, this was the eigenvector corresponding to 1, that column.
Okay. Yep, that sure is.
And this was the eigenvector corresponding to 2, and that was the eigenvector corresponding to negative 1. For that reason, the order in which the eigenvalues are going to show up now is going to be 1, 2, negative 1, and you're going to 0, 0, 0, 0. There you go. That was your initial matrix A. That is the transition matrix. That is the inverse, and that is your diagonal matrix T. And everything is in place now.
That makes sense. So then, final questions. For the problem in 2, I would just have to make sure, like, that there are zeros in a certain form, or like either I would say the upper triangle form or the lower one, there would have to be zeros in order for me to like actually.
Look, the only difference with the homework problem that we discussed in the beginning is that the matrix is not triangular. However, we showed how to find the eigenvalues. Once you find the eigenvalues, the process is the same. And in that process, the least of our worries is that we have a triangular matrix. So when I say in that process, I mean when you do this thing right here. When you go eigenvalue by eigenvalue and you find the fact that you have the triangular pattern here doesn't really matter. You still have to do the Gauss elimination method. Okay, so you might not have those triangular patterns, but you will do the Gauss elimination method for whatever matrices are going to emerge. That's what it is.
Oh, okay. So then I won't even, I mean, in class though, you said I would have to find the determinant, or I would have to use the determinant form.
Yeah, to find the eigenvalues. I mean, if you look at it, we already said what was the if you look at the matrix that you get for let me see, what is the homework. So the only difference is that exactly because it's not triangular, you need a little bit more work. I mean, you're going to get something like that. So if you do determinant of lambda I3 minus your matrix A, then this is going to be lambda minus 1, 0, 0, 2, lambda minus 1, 3, and then minus 1, actually negative 3, minus 1, lambda plus 1. So now this is something that it's pretty straightforward to compute because you have lambda, because you expand with respect to the first row. You expand the determinant with respect to the first row. And this is what you get. And now this thing is going to be a polynomial. This thing is going to give you a polynomial of the second degree, which you can solve using your quadratic formula. So lambda minus 1 times lambda plus 1 minus 3, which gives you lambda minus 1 times, I bet you it's very straightforward. So it's lambda square, it's lambda square minus 1 minus 4. So it's lambda square minus 4 which gives you right away lambda minus 1, lambda minus 2, lambda plus 2. So your eigenvalues here are going to be 1, 2, and negative 2. So you will have to do the work that we did. And like I told you, when you found the eigenvectors, it didn't really matter that you were working with a triangular matrix. That didn't matter.
Okay.
Okay.
Oh, okay, that makes sense. And then for the last thing, you said that in order for us to find out if it's diagonal, it's able to be diagonalized, we have to make sure.
This is diagonalized. This is diagonalizable for sure. Why? Because
Oh no, not this one.
Oh,
yeah, not this, not number 2. I'm talking about number 3.
Yeah, for the last one, we said that you pretty much narrow it down. If I remember well from class, it was the numbers 0 and 2. So if it is not diagonalizable for a value of a, that has to be 0 or 2. And you just have to do the work for a equals 0 and a equals 2. And if memory helps, for one of them, it's going to be diagonalizable. For the other, is not going to be diagonalizable, which means that eventually the answer will be just one number.
Okay, that makes sense.
Okay.
Thank you so much.
You're very welcome. Have a great weekend.
You too.